Here's question 2 from the practice test. You can see I drew the solution curve through the point 31 because that's the curve we're going to need to look at for part C. But anyway, they gave us our differential equation, slope field is drawn, and they are defining f of x is the particular solution that passes through the point 31. So that's the particular solution when they refer to f of x. So part A, use the line tangent to the graph at x equals 3 to approximate f of 3.2. So the point is 3, 1. We have to get the slope. Slope, remember, is dy dx. And our dy dx is 1/16 y times y squared minus 9. It's y, so you have to sub in your y values. A lot of you were using x values. You cannot make mistakes like that. Okay, sub in your y values. We get negative 8 over 16, or negative 1/2 is our slope. So there's the equation of our line. Here's where we sub in x, and we use 3.2 because we're looking for the approximation at 3.2. So we get y minus 1 equals negative 1/2 times 0.2. Y minus 1 equals negative 0.1. Add 1 to that. You get f of 3.2 is approximately equal to y, which is 0.9. Show that approximately equal to. Okay. 2b, find f double prime of x. Okay, and then we want to know if it's an overestimate or an underestimate. So f double prime is taking the second derivative. It's implicit differentiation, so product rule. The derivative of the first, so 1/16 times dy dx times y squared minus 9, plus the first times the derivative of the second, so 1/16 y times 2y times dy dx. And then I just subbed in the dy dx. We leave it like that. We want to know at 3, 1, is our tangent line an over or an under approximation? Remember, we know if it's an over or an under approximation, a tangent line, if our curve is concave up or concave down at that point. So we evaluate our second derivative at the point 3, 1. Again, it's in terms of y. We're only subbing in the y value of 1. And we already know from part A that dy dx is negative 1/2. So we sub in our negative 1/2 for dy dx, 1 for y, and we get that our second derivative is 3/16. So since that second derivative at the point 3, 1 is greater than 0, the graph is concave up and the tangent line is an underestimate. If the graph is concave down, the tangent line is an overestimate. Part C wants us to evaluate the limits to infinity and negative infinity. Here's where we talk about this graph. And once you see that particular solution sketched in, you look at the limit as x goes to infinity, y is at 0, it's a horizontal asymptote. As x goes to negative infinity, y is at 3. Remember, the definitions of horizontal asymptotes are limits as x goes to infinity and negative infinity. You have to look at the sketch on the graph. And then part D, which initial conditions y of 0 equals k lead to particular solutions that are increasing as x approaches infinity, and justify your answer. Oh, again, so increasing means positive slope. And we're looking at the graph at x equals 0 because it says where y of 0 equals k. So we're looking at the y-axis. And where do we have positive slope field lines on the y-axis? In here and up here. So how do we describe that? Well, it's when y is greater than 3, but remember, back here, y of 0 equals k, so that means k is greater than 3. And it's also when y is between negative 3 and 0, but again, y is k, so it's when k is between negative 3 and 0. So I think this question is good. It's a great practice for differential equations, but you have to be careful. I think this was a question of reading carefully and using y's where y's were important, and and that using that particular solution 3, 1, that was the key to the whole question. Okay, so there are our solutions.